Y27 quantum bound states. In quantum mechanics, it is just like Newtonian mechanics, total mechanical energy of a conservative particle under conservative force is conserved. Okay, this energy conservation has been tracked experimentally. Therefore, we assume that time derivative of Hamiltonian, that Hamiltonian is the total mechanical energy, is conserved. So it's a constant of motion. In addition, we copy the formula of total mechanical energy coming from Newtonian mechanics. However, what we have to do is to consider the wave function. Most general case is the state cat instead of wave function. Wave function is a special case. Just like a vector in Euclidean space, the quantum state constructs a vector space called the Hilbert space. This is a Hilbert space of vector. The Schrödinger equation is nothing but a copy of this equation, except that the energy is obtained by taking the time derivative operator of the over vector IH bar to the vector defined in the Hilbert space. And if it is an eigenstate, the characteristic state, then it will give the energy eigenvalue by acting this operator. In the configuration space called the coordinate space, this potential energy is a function of position. Therefore, it is the same as the classical mechanical value for the potential energy. However, because we are acting this operator to the wave function over state cat, more general cases state cat, this one behaves like an operator that is the spatial derivative twice of a spatial derivative that is a Laplacian. Especially, we have h bar over I squared to make the dimension the same as the momentum. So, as a result, if we project the position space that is expressed in terms of wave function we are we are familiar with, just like e to the k dot x minus omega t, this kind of wave function, and this state cat defined in the Hilbert space becomes just like wave function. So wave function has the space-time dependence, and by acting this operator, time derivative operator, we collect the energy. Another way to collect the energy is to make use of momentum. Actually, this is wave vector. That is using the Hamiltonian operator in the coordinate space. In the coordinate space, potential energy is identical to each other. However, in this operator, in the configuration space, becomes a derivative operator. And actually, because the system can be either described in a coordinate space or in the momentum space, and if we describe the system by projecting the momentum space, in that case, this one is a number. Instead, this position-dependent potential energy becomes the operator that is the derivative operator with respect to the momentum. And actually, this strange idea comes from Dirac, and this is called bra. That actually that is the multiplying the unit vector on the left-hand side as a scalar product, similar to this action. And right side, this part is called cat. So in the matrix space, the bra is nothing but uh, transpose of wave function and take the complex conjugate. It is a Hermitian. It is called the Hermitian conjugate of a matrix, a column matrix that is for this wave function represented in a matrix space. And this column vector represent the cat, and this one is represented by its transpose, becomes row vector, and take the complex conjugate. Degrees of freedom and phase space. In classical mechanics, we use the word phase space. Phase space is, for example, in one dimension, one particle motion, then the degrees of freedom is just one. And that means we need only a single coordinate, and is in addition, there should be a momentum that these two are called conjugate, just like 1 plus the square root of 2 and 1 minus the square root of 2, they are conjugate. 1 plus I and 1 minus I, they are complex conjugate, something like that. So it is always a pair. In classical mechanics, this coordinate and conjugate momentum P, construct what? Phase space. And phase space is usually of this single particle involves 2 degrees of freedom. 1 degree of freedom comes from the coordinate. The other degree of freedom comes from its conjugate momentum. And if you know both of them exactly, then we know the classical path. The circle is a phase space diagram of a harmonic oscillator. We know potential energy and kinetic energy is constant. We rescale them, then we find the ellipse, something like some constant and momentum divided by some constant square equals 1. This is an ellipse. This is a phase diagram in classical mechanics. In classical mechanics, we know this x and p simultaneously. Therefore, if we solve the problem, we know when the point on a phase space, the system is placed exactly. In case we have n particles and 3 dimensions, then we need 3 times n spatial coordinate xi's. In general, we can use q instead of x. For example, the coordinate can also be, it can be a Cartesian coordinate, but in general, we can introduce an angle. For example, the polar angle and azimuthal angle, that can be an equivalent coordinate. So q does not have to be the same as Cartesian coordinate. So we n particle in 3 dimensions, we have 3n coordinates, and each coordinate has its own conjugate momentum. Therefore, if we are describing n particles in 3 dimensions, we have many variables, that is 6n degrees of freedom, 6n degrees of freedom in phase space. In general, this is a 6n dimensional Euclidean space, something like that. However, in classical mechanics, we have the relation that is called the Poisson bracket, but it is equivalent to the quantum mechanics. There, this momentum and coordinate has, as soon as we replace this momentum in terms of a derivative, if x appears first and p appears later, and this is called a commutator. And actually, on the right side of this object, we have a wave function. So we need to take an operation onto this function. However, if we substitute this one, what we find is I h bar x partial derivative and partial derivative x and something. This one, it's fine. However, this one is actually this. And if you take the derivative, you have two terms. First term and second term. If you take the derivative of the first factor, it is just something multiplied by 1. And the other term is x times derivative. And actually, this is this. And this term is identical to this. So this was subtracted by the other term. And therefore, the final result is minus 1 and something. Minus 1 is multiplied. So I have IH bar. Here, A and B, they can be different. For example, A equals B equals 1. What we have done is A equals B equals 1. Yes, this is IH bar. However, what happens A equals 1 and B equals 2, X H bar over I, Y derivative, and Y derivative X. And X and Y derivative, that's fine. They can commute. Y does not feel any change in X. Therefore, it is a 0. Therefore, what we find is if you compute some quantum mechanical wave function as a product of position and momentum, what you find is we have a strange term. This appears if the coordinate is acting on the conjugate momentum. If the coordinate and conjugate momentum has different indices, for example, x and y momentum, then that's fine. They commute. So because of this non-vanishing commutator, we call this as commutator, there is uncertainty emerges. Let's see. If, if there is a physical variable, any physical variable should be expressed in terms of phase coordinate. we know X and P. For example, energy is a Hamiltonian. Hamiltonian is expressed as the sum of kinetic energy and potential energy. What we find is momentum appears here and position appears here. So mixture, it is a function of coordinate, and conjugate moment. And if a physical variable is measured in a quantum system, we have an eigencat that represents a quantum system. This is just something like a vector, but it is a vector in Hilbert space, not a Euclidean space. And Hilbert space is something like a vector, column vector, whose elements are complex numbers. And this is a cat. And just like what we expand in the basis vectors in the Euclidean space, Hilbert space vector that represents a physical state is a linear combination of various basis vectors. By the way, this operation, and this operation is not a mathematical, it can be understood as a mathematical one, but it is a physical measurement. All physical measurement represent this operator is represent physical measurement. This one shows that if you measure a quantity, momentum, mass, whatever, then its value is not a single value, and there is a list of numbers that represents, for example, spin of a particle, either spin up or spin down, something like that. So measurement will give, in general, a limited element. And the state, for example, 1, 0, 0, this one gives A equals A1, A2, and they are assumed to be all different. Therefore, this cat represents the physical states with the eigenvalue. Measured value is called eigenvalues. Physically measurable quantity whose value is called eigenvalues. So, completeness relation. In three-dimensional Euclidean space, we can express any vector as a linear combination because this is a matrix form, for example, 1, 0, 0, 0, 1, 0, 0, 0, 1. These are basis vectors. In quantum system, just like a Euclidean vector, they are orthogonal. These are, they are just like perpendicular to vectors in the Euclidean space. Their matrix form is something like this orthogonal. If you multiply 1, 0, 0 and 0, 1, 0, this multiplication will give 0. And 1, 0, 0 and 1, 0, 0, this is 1, something like that. So this bra represent this, and the cat represent this. Again, chronicle that they are quantum states. Quantum states with different eigenvalues whose measured values will be orthogonal, just like the orthogonality of the unit Cartesian basis vector. In addition, we have completeness relation. Completeness relation is this. If you multiply the unit matrix, you don't change any vector. That means this multiplication and sum, the first the second term and third term. This one gives x component, y component, and z component all combined. Then this reproduce any three-dimensional vector, something like that. Therefore, this completeness relation says any quantum state is a linear combination of allowed states that are called state cat. In a matrix representation, they look like Euclidean vectors. However, all of the components are assumed to be a complex number. Max Born introduced a statistical interpretation of this quantum state. Just like a scalar product between two Euclidean vectors, we can define the scalar product between the two quantum state that is called cat. And if you multiply a scalar product in a matrix space, we usually take the transpose and multiply, and it becomes a number because this one becomes a column vector, B1, B2, B3, and this guy becomes a row vector. Just like that, cat has a conjugate bra, and this is cat. If they meet together, just like what's happening in the three-dimensional Euclidean vector, they become a scalar product. By the way, just like the unit vectors I and j in the Euclidean space, they are orthogonal. Therefore, sum of many components, we can see here if there is a complex coefficient, this bra has an additional operation that is complex conjugate. Therefore, if we sum all together, these are all independent. However, we have orthogonality that A, P, and AQ, only the two cats with the same physical eigenvalue, measurable value, survives. Kronecker delta appears, so only the diagonal piece is remaining. And every term has the probability of finding the state with the eigenvalue. Therefore, if it is the partial probability of any measurement becomes 1. It was given by Max Born. Okay, if it is a state cat's square scalar product itself is always 1, because this is nothing but the probability of existence of a particle, or quantum state. So if it exists, then it is 1. If it doesn't exist, then it is a 0. What about the average value of a physical measurable? As you know, in quantum state, of physically measurable quantities construct a set. They are called eigenvalues. And therefore, because the measurement will give, every measurement may give different values, we have to take the average of the all allowed eigenvalues. In that case, because this guy represents the probability, we average the physical value of this measurement over all possible eigenvalues. And because this is an operator whose eigenvalues are A, the final result will always survives only if the two eigenvalues are the same because of the Kronecker delta. This is the average of eigenvalue for the measurables. If there are physical measurables, two measurables, whose commutators are zero, then we say compatible. As we know, x and y, their commutator, 0. X and py equals 0. However, x and p is not equal to 0, but IH bar, something like that. If the commutator is 0, then these two measurements can be done with extreme accuracy. That means whether we measure A or B, the state doesn't change. It remains the same state, and the measurement will give the same value, whether we measure B first or A first. The final result will be the same. It is true for the compatible operators. However, if the operators are incompatible, just like X and P, if it is non-zero, it is impossible to have the eigenvalues remaining after the operation. The operation of A will change the eigenvalue of B. Operation of A does not change the eigenvalue of A. However, it does change the eigenvalue of B if these two operators are incompatible. This is the main source. This commutator non-vanishing commutator is the source of uncertainty principle. In the matrix space, we use a column vector for the cat and row vector for the bra, but it can also be used as a wave function. In case, just apply this unit operator. This is a unit operator. If you apply the unit, insert the unit operator between them, and we define the projection of the state cat onto the space, we define a wave function. And it's a complex conjugate, can be just to switch it one. It's a complex conjugate of wave function. So this is a matrix form, and this is an integral form. Therefore, this one is identical to this. Schrödinger equation in configuration space is we have the we insert this operator. In that case, this equation for the state cat becomes the equation for the function, wave function. And I told you, wave function is just a position projection of a state cat. And in that case, it becomes function of x. And the kinetic energy becomes the operator that contains the Laplacian. Okay. This one is comes from the Max Born's statistical interpretation. Wave function must be continuous. If the wave function is continuous, we can derive the Snell's law. Just the continuity requirement is enough. In addition, in a bound state, the bound quantum system must be quantized because of very strong postulate. The detail can be found explicitly. The time-independent Schrodinger equation derives from the time-dependent Schrodinger equation. This is time-dependent Schrodinger equation, time derivative operator. As you can see, time derivative operator, there is a spatial derivative operator. They are divided into separate terms. Because of this nature, we can always factorize the wave function as a product of time-dependent factor and space-dependent factor. Okay? The reason is that if this is x derivative, just x and time derivative. So this x derivative and time derivative, they are separated into two pieces as a sum. If there is something like that, this operator appears, we cannot factorize the solution. This is a trick that is usually used in solving partial differential equation. Therefore, if we substitute this one into time-dependent Schrodinger equation, what we find is this. You can find the left-hand side depends on t only, right-hand side depends only on x only. Therefore, these two values must be independent of time and independent of position. Therefore, it is a constant. And this constant is called energy eigenvalue. So we put this one to be E, and we can solve this, separately. Spatial dependent part is called time independent Schrodinger equation. And if it is E, the solution of this first order differential equation is trivial. As a result, we can combine all of the time-dependent factor and spatial-dependent factor to construct the full wave function for any position and time. Okay. In classical mechanics, if there is a potential, kinetic energy becomes negative above this line. This is energy, and this is potential energy. Therefore, this is physically allowed in classical mechanics. However, in quantum mechanics, our kinetic energy becomes negative, and that is allowed because it is a wave. The solution, if we remember the solution for the harmonic oscillator, damped harmonic oscillator, some case your solution is sinusoidal, and some case you have exponential decay. This one appears in this case. If the energy is greater than the potential energy, that's fine in this region, then this equation looks like a harmonic oscillator, oscillating. If energy is less than the potential energy, that means this. Total mechanical energy may be less than the potential energy. That means the kinetic energy becomes negative. In that case, it is not oscillating anymore. Instead, it becomes exponential. Okay, so either exponentially decay or increase. Sure, if it is a wider region, it is impossible to have the probability increase arbitrarily large. Therefore, you have a potential barrier. In that case, your wave function will decay. and at large distance, your wave function eventually vanish. Infinite potential well is a very good example to show the quantum states, quantum bound states. We have two solutions. In the middle, there is no potential, therefore it is a sinusoidal wave. However, outside, the potential energy is infinite. If the potential energy is infinite, it must not stay there. It is potential is a finite, wave function decays. However, if the potential is infinite, this decay becomes very fast and it is impossible to survive outside of infinite potential energy. Therefore, if there is an infinite potential well inside the free particle, outside of this potential well, wave function must not survive. Therefore, outside is a zero. Free particle is a sinusoidal function, and endpoints, both endpoints, where our wave function must be zero. However, Max Born's very important postulate that wave function must be continuous. Then, the only continuous free particle state is this. And then we have additional resonances. They are exactly the same as what's happening in the musical instrument in classical mechanics. This is harmonics. So these are quantum states, and this eigenvalue n determines a momentum because n pi over L is the wave vector, wave number, and from which we can determine the energy and so on. And what we can see is the scalar product between the two quantum states is orthogonal, exactly the same as the Kronecker delta, whatever integers are substituted. Therefore, a quantum state, an electron inside of infinite potential well, must be a linear combination of these various quantum states. And if you want to express in terms of a Bryan cat, it's fine. If you want to express in terms of wave function, projection onto the position space, your value is square root 2 over L sine n pi x over L, something like that. You have infinite number of eigenstates, and they are all orthogonal to each other. This is the Hilbert space. This is different from Euclidean space, but it is a very analogous to the Euclidean space. Instead, Euclidean space, we were living in 3 dimensions. However, our dimension of this Hilbert space that represent the wave function of an electron is infinite dimension, and it is countable because these are integers. And all those eigenvalues allowed measurable for the total mechanical energy is the kinetic energy, and they are completely expressed in like that. And expectation value, I can compute the expectation value for the momentum. For example, momentum expectation value is always 0. Why? The wave, sine wave, is sum of e to the ikx and minus ikx. Probability of finding the wave to the right and the probability of finding the wave to the left. This is a standing wave. So energy flow, momentum flow to the right and to the left, they are equal in probability. The two probability cancel exactly. So our average value for the momentum must be exactly 0. In case our electron is or linear combination of two possible states, either n equals 1 or 2, and we have a factor something like that, probability of finding each state is 1/2, 1/2. You know, C absolute value squared represent the probability. And there's a table that shows the momentum, and the probability of having such kind of momentum is given here. And even if you multiply any unit modulus complex number, that doesn't change the probability. So complex phase doesn't contribute to the probability of measurement. Okay,